Yeah, leave the room, the PowerPoint slides and go to something profitable in your life. Hey. We're lost cases. Okay.
You still have 2 minutes.
Everyone who was here late yesterday gets bonus points. That includes Danny, who was not gonna come, or ashamed to come.
You convinced me, that's right.
Yeah,
Only took a beer.
there you go.
Hey, this is being recorded.
Okay. Well, it's it's 9 AM by my clock.
Yeah.
I gotta get this started. Yeah. Welcome everyone to the morning session. This is a session on type 1A supernovae and supernova remnants, and our first speaker is here in the flesh. And it's I was saying so.
Evo, like
Evo.
evolution.
Evo said.
Thank you. Thanks, Carlos. Yes, so I'm Evo, and this is my talk title: Fresh View of Type 1A Supernova Remnants. Not super fresh anymore, just a few years old, but still reasonably fresh. So let's start with some front matters. I'm in Australia at the Australian Defence Force Academy, University of New South Wales. Great place to visit. So if you're ever, visiting ANU or something like that, come stop by as well. We can host you for a few days, most likely. And so where is Canberra? You might be wondering, where's that? And the more important question, are all the animals poisonous? No, just most of them. So Canberra is right there. It's the capital. A little bit like Ottawa, between the two big cities. There's also cute animals like wombats. This is up in Canberra, or giant monitor lizards like this lacy, about 2 meters on a giant tree, and kangaroos on the beach. So, lots to see. The big question of what I'm after is still, after all these years, what are type 1A supernovae? And I'm going to just, categorize them simply. But the one other question is, are they Chandrasekhar masks? That's what people used to think. So 1.4 solar mass or close to it. You get very high densities. Well, adding just a little bit more mass to the surface, the white dwarf is going to shrink a lot, get very dense in the center and ignite, and maybe get something like a delayed detonation. Or are they from primary white dwarfs that are below the Chandrasekhar mass, maybe 1 solar mass or 1.1, for example, for merging white dwarfs. And the person who put me on this problem really is Jim Truan, who sadly passed away this year, earlier this year in March. And Jim taught me a lot of nuclear physics, a lot about supernovae. Most of what I know about that is from him. But he's also taught me how to be, a researcher that enjoys his work, and how to enjoy interacting with other people, and how to not take things too seriously. And he his favorite quote I have 2 favorite quotes. One's that Evo, we're here to have fun, and the other one is, use me like a credit card, charge me now and pay me back later. I'm not sure I ever paid back all my debts, but Jim, rest in peace, and thanks for everything. Okay, so these 2 major categories, on the right, simulations of delayed detonation, which start the turbulent deflagration, expands this very compact star, so we get some mass at densities, above 10 to the 8 grams per cubic centimeter, significant amount of mass, so that can burn, above 10 to the 7, so that can burn to silicon group elements, which we need for the spectra. On the right is a simulation of sort of a double degenerate channel I don't actually want to explain the simulations in detail because that's not what I'm talking about today. I just want to say that, for almost 15 years, I basically worked mostly on the energetics and how to model the energy release and nuclear fusion and how to calculate the nuclear synthesis in models like this. For this talk, just want to suffice, it should suffice. I want to say, okay, on the left-hand side, primary mass is Chandrasekhar mass. Ignition is, through quick nuclear fusion reactions of carbon-12 high densities. And on the right, we have primaries around a solar mass. And ignition can occur in different ways, violent accretion stream that, triggers a detonation, or maybe you get a helium layer that detonates first, and then that convergent shock triggers a detonation in the core of the more massive COY dwarf, which blows up the primary and maybe the secondary or not. I'm well aware, yes, there are many other proposed models. This is illustrative. I just want to phrase this sort of the big question. One of the big questions, and it's not simple to answer, what is the mass of the white dwarf when they explode? And it's probably, there's a range of masses, there's different type 1A supernovae, but one could ask that question for Tycho or for Kepler or for other things. What was the mass of that white dwarf? Was it a solar mass or, near Chandrasekhar mass? So let's move on. One thing we've done over the years with mostly the MPA group and other collaborators is to run these 3 hydro simulations and then run the result through a nuclear reaction network, and then run that result with the final structure of the simulation after about 100 seconds or so when it's in homologous expansion, run that through a radiative transfer code, and generate a time series of spectra. And we can compare those with observations, and that was, I don't want to say the holy grail, but this is kind of the industry of sorts of the type 1A supernova simulation business. And so on the left-hand side, there's a delayed detonation model in black with a gray band showing the viewing angle, dependence as you look at the supernova from different sides, becomes more and more less viewing angle dependent. In red is an observation of supernova 2011 FE always at the same epoch. And you can see early times it matches quite well. On the right, you have a merger from Rudiger Puckmore in this case, and there the early spectra don't match well, but they match much better at late times. So why am I showing this? Well, basically, I'm saying, well, we haven't solved the problem. Right? I mean, Jim said, I've been working on this problem for 40 years and I haven't solved it. I'm getting worried. I've been working on this problem for maybe a little over 15 years, but I'm also at the same, we haven't really solved it yet, but we're making progress. The point is the comparison can be inconclusive, and so we're thinking about other ways to attack this problem from a different angle. And so here is just an outline sort of how we think about the type 1A problem, or how I think about it. So we kind of start with a progenitor model, like, okay, some ideas from the 70s, typically, some white dwarf merge, or, you accrete from a red giant or some other compact object, maybe even a sort of B star or whatever you're accreting. And so that's your progenitor model, like what the path to explosion, right? And you can model that with rapid binary evolution to say, how many of these do I have, and get some population statistics and get rates and delay times for these systems. That's kind of what my wife does, Ashley Reuter. And then you get to an explosion model, which is different from the progenitor channel. But the explosion model could be deflagration to detonation transition in a near Chandrasekhar mass COY dwarf. You do your 3D explosion simulations, and you do your calculation of the nuclear synthesis, which gives you some sort of 3D structure and evolution. You get all the velocities and at a certain time, density at a certain time, and the composition, and all your radioactive isotopes. And so you can do your radiative transfer, your model spectra, and you compare that to your supernova, and you scratch your head and you say, well, sometimes it works, sometimes it doesn't. We don't really know. We've done this for several decades now, and we don't know. So that's sort of the existing pipeline, I call it. It's sort of a production pipeline. We cover those steps, and we go from the model to the observations, and we haven't solved the problem. at least not to satisfaction. And so in green, I'm more the, current and future efforts of what I'm thinking about, which is, okay, well, let's think about the environment too, right? You have your progenitor model, so there's mass loss from these systems which shape the environment, which what the supernova explodes into. Very important for supernova remnants, as you all know. Then like you connect the environment to the supernova remnant, and what I'm trying to do in the next few years is to basically use our actual simulations in 3D and have evolve them in 3D to the remnant phase. And Jules Ferrand will talk later today. Of course, he's done that already in 3D and compared to Chandra observations of picked out how the models differ. But what we want to do is basically have predictions of these coronal lines in the optical that I will talk about today. So it's another type of spectrum, just not of your supernova. It's a spectrum of your supernova remnant in the optical, and that's what I'll get into now. So I call it supernova remnant tomography for a reason I'll explain later. And so it's a somewhat newish diagnostic. Optical coronal line emission of the reverse shock ejecta of young type 1a supernova remnants. So before we found this in 2019, I was always like, these oxygen-rich supernova remnants and the Kokolov community, they have it so nice. They can look at the ejecta of their Kokolov supernovae and study them with optical telescopes, which I'm more familiar with than radio telescopes, for example. And I was always like, why can't we do that for type 1a? And so I had a good talk with Mike Doppeda, who also sadly passed away recently. And he was basically like, well, there should be optical emission. It's just going to be very faint. So we'll never see it. But the whole we'll never see it is like, well, we don't see it until the telescopes are big enough and the instruments are good enough, and then we'll see it. And so that's kind of what happened. So a fresh view. So you may ask yourself, most of you probably know, but what are coronal lines? When you're talking about coronal lines, well, we just call them coronal lines because they happen to be visible in the solar corona, right? So these are basically mostly low-lying forbidden transitions of collisionally excited and often very highly ionized atoms emitting in the optical and other wavelengths. Famous examples are, the green line of iron 14 or red line of iron 10. And so it's sort of, when I first learned about this, I was like, that's interesting. So you have this gas that's like 10 or 20 million degrees hot. You'd think it should be just all X-rays. But then you observe it in the optical, which, right? The optical is like the black body temperature is like 6,000 degrees, not millions of degrees. But it's just all very non-equilibrium. Key instrument is Muse. It's really cool, but I don't think I have much time to talk about it. So it's an integral field spectrograph that gives you approximately 110,000 spectra at the same time over an area of roughly a square arc minute. So let's go to the LMC. Here's the LMC. Here's the supernova remnant of 519, 69.0. And this is what it looks like, 20 arc seconds or so. This is the scale bar up there, which at the LMC is almost 5 parsecs. And in blue, we see, the bomber-dominated emission from the forward shock, so the broad and narrow bomber lines. And in red here is sort of broadband Chandra X-ray. This is, for example, iron K alpha. And so the general pictures, you have this forward shock going out, and behind the forward shock, you have your non-radiative bomber emission, and then you have a reverse shock going in, and that's shocking the ejecta, and so then we found behind, in between, we found the iron 14, kind of where it should be, between the reverse shock and the more highly ionized iron emitting and X-rays. The good thing about optical studies is that the spectral resolution is very good, and so So we can resolve these lines, and here's, just an extracted from one of the points in there. It's very low surface brightness, as you can see, just scale like 10⁻18 arcturus per centimeter per second per angstrom. But you can resolve these lines and you can fit their widths. In this case, at 2,500 kilometers per second. Here's another remnant of 509, minus 67.5, same color map, bomber and H alpha and X-rays. And again, here's the iron 14, a bit broader, bit faster velocities here in the reverse shock, over 4,000 kilometers per second. So, why do I say velocity of the reverse shock? Let's do some back of the envelope estimates. So this is a collisionless shock, and from the strong jump conditions, we get this basically mass proportional heating of our shock ions. So KT is about 3/16 m times the shock velocity squared. But behind the reverse shock, you just have an ideal gas law. It's an ideal gas. So 3/2 KT is 1/2 m V thermal squared. And so combining both equations, we basically get that the shock speed dictates what the thermal width of your lines are. So the forward Tough max of your line remembers what the shock speed was at the time when it was shocked. Not what it is now, because it takes some time, which can be hundreds of years until the line is visible. But because there's no radiative cooling or anything that's very important, the velocities don't change very much. Of course, this is somewhat modified through like ion equilibration and things like that. But for very young supernova remnants, as far as I understand, this is minor corrections. Right. So together with Ralph Sutherland, then we've done some shock model calculations. I mean, he's done them. So with mappings 5, he does an incomplete fast shock. So basically, 3,000 kilometers a second or something, running into something like the expected density of the ejecta at the time. And you can see here how the fractions of different ions are emerging with time. So the collisionally ionized behind the shock. And so it takes a long time because that's of the collisions, right? It takes you like 300 years or so for these parameters to form 11 times ionized sulfur. Sulfur 12 is what you'll see. And here's the same for iron, right? You get the iron 9 very quickly after 50 years or so, but it takes you, 300 years to get ionized all the way up to iron 15. For example. So there's this progression of ionization states behind the reverse shock, all the way up to you're almost a fully ionized K alpha emitting plasma that you're probably very familiar with, or some of you, anyways. Right, and so there's a distance then that correlates as well, because it takes time, but in the same time the reverse shock keeps moving, and so the things fall behind, and there'll be about several tenths of a parsec behind the reverse shock, which is for a remnant because the reverse shock is moving in. Behind means for the outside. Right, and so a mu spaxel is 0.2 arcseconds, and so at the distance of the LMC, that's about 0.05 parsecs. And so these separations here, they're actually several spaxels, and so you can resolve this, right? The things are like arcseconds apart, and that's something you can resolve. And so why do I call it tomography? Well, tomography is imaging by sections, or sectioning, or through the use of any kind of penetrating wave. So in this case, it's penetrating wave as photons coming from these different ion species, and we're imaging the ejecta of the supernova remnant. Well, it's not quite like medical imaging because we can't say I want to look at this layer now. So I need to use the lines we have, right? And so these are lines, but the important thing is the lines for different depths of the ejecta. And so this is from the 2019 paper. In blue, we have better signal noise now, so it looks better, but I haven't made the plot, so it should look better. But so in red you see sulfur 12 furthest on the outside with the largest ionization potential. Then iron 14, on the left, this is sort of nice and bright and chalk. The iron 14 in the middle, and then the iron 9, which has a much lower ionization potential, is much closer to the inside. So forward shock going this way, and reverse shock going in, and we get this, this time behind it. So, the sulfur 12 would have been shocked maybe 300 years ago or something like that, whereas this iron 9 just much more recently. So ejector mass, ejector kinetic energy, and the ISM density, there's other parameters, but they're the key parameters that govern the evolution of a young supernova remnant. And so for fixed time t, let's say we know the time, we knew it, then the forward and reverse shock positions and velocities, they constrain the ejector mass and energy and the ISM density. And so moreover, for type 1a supernova models, much more so than for quark-collapse supernovae, I think the ejector mass and the energy they're really not independent. Especially for pure detonation, if you increase your primary white dwarf's mass and you detonate that, it's sort of, once you fix the composition, it's given how much energy you're going to get out. You're going to get out more energy because you burn more mass than ion groups, so that it releases more energy. And the reverse shock evolves more slowly for larger ejector mass. Yes, larger ejector mass means higher kinetic energy, which would make it evolve more rapidly, but they compete with each other, and it's really the specific kinetic energy that determines how quickly the reverse shock evolves. So how much energy do you have per mass? And so what that meant, so Martin Lamming ran some Blasphemer models, and so for 0509, that meant because we know how old it is, 300 or 400 years, there wasn't enough time for what we think the ambient medium density is to ionize all the way up to iron 14 for Chandrasekhar mass model. Right, there's not enough time because we know the ambient medium density is low, and we know we see iron 15 and sulfur 12. And we try a Chandrasekhar mass model with reasonable explosion energies, because you can't just tune it up, right? And it doesn't work. It doesn't ionize to iron 15 because there's too little kinetic energy per mass. And that's in that paper. And so, oops, out of time. Well, what am I saying here? I guess 0509 was subchandra then, because it couldn't happen. It couldn't happen Chandrasekhar mass. So that's the conclusion. And Ashley tells me that's often lost in my talks. So I'll try to make it very obvious now. But 0509 was 91 T-like, and it had a high kinetic energy, explosion energy, didn't it? It did, right? Yeah, so what? Yes, it was 91 T-like. Yes, it had high explosion energy. That doesn't mean it had to be Chandrasekhar mass, because the 1.1 solar mass detonating to your white dwarf can also give you over 1.5 beta, and it can give you still some silicon group and sulfur elements. I guess, yeah, so I like the way you make me feel. So that works, I think. Or show me that it doesn't work. I mean, I'm aware of the sort of controversy, but I would stick my head out and say yes. I actually believe that prediction that 0509 was subchandra, although it was 91 T-like. Shock velocities are time dependent. It's not the best plot to really show this. I just ran Leahy's Supernova Remnant, Python package evolution calculator, and in red you see the forward shock, and blue the reverse shock, indicated just the transition when you transition a set of halo phase. But you can see, I guess you will have to see how the slope changes. So there's a change in the slope of the reverse shock radius, and so the velocity changes with time. And so what that means is that because we're probing, right, the reverse shock velocity is related to the width of the lines. And the lines, where they have iron 9, iron 15, they probe for the reverse shock that 50 years ago, or 500 years ago, or 400. Then if we can fit those lines, then we get a time evolution history of the reverse shock. All right, so that's exciting. I only got 3 minutes. I'm going to speed up to my last slides. I just want to show some more preliminary things, but so things are evolving. We have a deeper Muse cube now, higher signal to noise, and so we find other lines. For example, fairly well, I believe this is calcium 15. And Ralph runs the shock models for some right now still kind of ad hoc abundances. We haven't really fit anything. It's just a test calculation to show principle here, but the calcium 15 actually does pop up. We also can see here on the right, so that's what I think is calcium 15 and the iron 14. The calcium here is just visualized, and it looks a lot more clumpy somehow. Let's compare it to the iron 10, which we now also find. Iron 10 is sort of nice around, very circular, thin, limb brightened kind of thing. But the calcium looks, I don't know, a little different. It's got all these, some of these things are stars, but this is not, and it's sort of got these filaments inside and more clumpiness, it seems. Not sure how to interpret that yet. So this is the line list of these coronal lines that we see, iron 9, iron 10, iron 11. So in red is sort of the new stuff that still needs to be written about and really investigate a bit more. There's probably a nickel 13 line as well. And one can go really fishing for a lot more in the infrared. There's some lines in the UV. And so I think it's for me, it's very exciting. I'm just happy to find new elements, because then, you can have a handle on the composition of the type 1a supernova. Was the calcium far outside or is it deeper inside and things like that? Eventually, I'm hoping will be something we can probe. Okay, so that brings me to the end. Basically, I've sketched how the optical emission from the incomplete reverse shock can be used to study type 1a supernovae in some reasonably novel way. An outcome is that 519, which we know from light echoes was a normal, so branch normal type spectrum, well matched by a Chandrasekhar mass model. And we're not saying that it had to have been that. It's just Martin can explain it with this. But for 509, the 91T like, we find it was best matched by subchandra, and couldn't explain it with a Chandrasekhar mass. Last but not least, all this work is collaborative work. I'm very grateful to all my collaborators, colleagues, for the contribution, mentorship, advice, encouragement. And for this work, it was especially Martin Lamming, Parviz Gavanian, and Ralph Sutherland. I come more from a nuclear physics background, so the atomic physics is something I need a lot of help with. And that's something these guys are really good at. So it's a good and fruitful collaboration. And last but not least, I guess, thank you so much for the invitation. I really appreciate it. It's my first time in Boston, and I'm really enjoying it. I think it's a great conference, and I want to thank everyone for listening to my talk, the people that did listen and came today online and in here. And come to Australia. This is another strange critter that was in our kitchen. It fell down the range hood, the little chimney. It's actually not poisonous. It does look like a gremlin, but so we're looking for PhD students. We've got good scholarships. There's opportunities for DECRA fellows, so postdocs as well. And talk to me if you're interested. Thank you very much.
Okay. Let's give beautiful timing. I did not monitor Zoom. I believe there's a question, but I did monitor Slack, and there was a comment from Craig Wheeler reminding you not to ignore spec poll.
Okay,
I'm just telling you.
so spectral observations of,
Type supernova, I assume.
yeah, no,
Maybe Craig can elaborate. There are a couple on Zoom, one from Martin. Ejecta clumping could also accelerate the progress of ionization because of reverse shock. But this is probably a better explanation for sulfur
well,
12 than for iron 15, because iron presumably inflates into bubbles compressing the surrounding ejecta. That's a good point.
yes, I guess higher density would increase your time scale for ionization, but
Yeah,
I mean decrease the time scale, but yeah, I guess the iron will be lower density. I guess that's what you're saying. Yeah.
are there any questions in the room? Danny has one.
I'm not in the type 1A community, so if you go back to the previous slide, I'm glad you put it there, so I got the thinking
This
straight.
one?
No, you
No,
put the conclusions.
Oh yeah,
Basically, for the second event, you're saying 91 T level,
yeah,
because I remember is more luminous than a typical.
yeah. It's more luminous and
And
it's
yet it's
shallow silicon and iron free.
Yeah.
Yeah.
So,
The luminosity has to do with the amount of nickel you make, right? And so it's actually easier to make a lot of nickel in a subchamber and look, like a 1A than it is for a Chandra second mass, because you just, if you detonate a 1.1 solar mass white dwarf, you'll make like 0.8 or something like that solar mass on nickel 56, which is on the high side, or 0.9.
If I may interject here, because so back in 2008, Armin found the light echo, which is 91 T-like, and we also published an X-ray analysis of this particular remnant. And because this was 2008, we didn't use the Chandra model, right? Because at the time nobody did. It wasn't fashionable.
yes.
Now the model that worked is a near Chandra model with almost a solar mass of nickel 56 for the X-ray spectrum of the remnant. Now, as Ivo very, very carefully pointed out, show me that it doesn't work, right? So we haven't done the detailed comparison with sub-Chandra models, so I can't really say. But addressing your comment, the model that worked at that time, those parameters had almost a solar mass of nickel. So,
But that's when it didn't have the reverse shock position and velocity, right? To try to match
No,
against. So
that is also true. That is also true. Now, from the work that we've done comparing Chandra and sub-Chandra models more recently, the parameter that we found really has the strongest influence is actually the ambient density. So you have to be very careful that your conclusions are not degenerate with that.
Yeah.
But I can't say anything more specific because we haven't done the work. Maybe somebody will. Where's Travis?
Here.
Work for you. Okay. Any other questions, or should we move on? No, then let's thank Ivo again. And a virtual contributor talk, 15-minute talk from Jules Bellon, who is going to give his talk virtually. See if we can get.
There it goes. Okay, you can share your slides when you're ready.
Hi, Jill.
Perfect. Thank you.
Are you in Japan?
So actually, no, I'm employed by the Riken Institute in Japan, but I'm currently visiting the University of Manitoba. So I'm in Winnipeg. It's
Well,
8:30.
that means it's not the middle of the night for you, which I guess is good.
No, it's early.
Take it away.
So we good? Okay, so my name is Gilles Ferrand, and I'm going to talk about this work we've been doing connecting supernova explosions and the supernova remnant. I'm focusing here on thermonuclear explosions, so for type 1A supernova events. And so we have all these models for supernova thermonuclear explosions. And so there's classically this distinction between the single degenerate and the double degenerate scenario. And so the basic idea is you have this wide dwarf about Chandrasekhar mass that's accreting and eventually explodes. And there's been this idea that it could be two wide dwarfs. And initially people were thinking probably a violent collision, merger of the two wide dwarfs. And then they realized that there are other ways of doing this. You can, in this scenario, actually have a double detonation of one of the wide dwarfs. And this is not specific to this double degenerate scenario. Even for single degenerate, the question, as I just said, is like, is it Chandrasekhar mass or is it actually sub-Chandrasekhar mass? And if it's Chandrasekhar mass, we're not even sure like how it starts, so the flame is propagating and things like this. And there may be even other scenarios to explore. And this is what we have as a theoretical context to try to explain something like what you see on the right. So this is Tycho's SNR, that's a well-known remnant, like a prototypical shell-type remnant. And we know this was a type 1A explosion. But so what kind was it? So how can we do this? So assuming we have typed the remnant already, can we do better? So we can use detailed X-ray studies, this has been mentioned already, to unveil some characteristic nucleosynthesis effects. So maybe we can tell apart the different scenarios. People have been looking, of course, for a surviving companion, and this has been essentially unsuccessful. And the point that I want to emphasize today is about the morphology. So do we have morphological signatures from the explosion on the supernova remnant? So to do this, I'm running simulations. And so for the thermonuclear explosions, just like for a core collapse case, the successful explosion, they're 3D simulations and they're quite complex. And so we ourselves, so I was more on the remnant side of things, and we're also doing 3D simulations to capture the instabilities that are happening during the remnant phase. And so typically we were starting with the models, initial conditions, which were simplified semi-analytical models. And so the question is, what happens if we use these more realistic models made by people whose work is to make the star explode? And so basically that's what we do. We take the output of a supernova simulation and in 3D, and we use it as input for the 3D simulation, for the simulation of the evolution over hundreds and thousands of years. And so basically a hydro code on a grid in an expanding co-moving grid. And so before I show you the results about this specific model that I'm kind of advertising, I'd like to quickly review what we had done before. And so we started with the group of Fritz Röpke, and so the first models we used were from the very Ivo who just talked. And so we started with the most like canonical model, so Chandrasekhar mass single wide dwarf. That's the N100 model, so that's the first column. The 3 rows are different viewpoints. And so N100 it's parametrization of the weight united, this N100 number. And you have also the second column is N5, which is showing more asymmetries. Okay, then I have added DDT. So these are delayed detonations. It starts as a deflagration, it transitions to a detonation, which is one favored model. But we're not so sure if the detonation will happen. So then they redid the grid with pure deflagration models, which is the 2 columns on the right. So N100 def and N5 def. And so here you're looking at a slice of the density to see the inner structure, and you're looking now at 500 years of evolution of the remnant. Okay, so you see what you'd expect from a supernova remnant. You see this shell structure that is formed. So I'm assuming you see my pointer, and you have the forward shock propagating in the ISM, the reverse shock that goes inwards, and you have this related of fingers. So instability from the SNR phase. And they will all converge in time, so to set of like solution, but you see that even after hundreds of years of evolution, you do see the imprint of the initial shape of the ejecta. And so specifically, like the N5 models, which were more asymmetric initially, they produce more asymmetric remnants. Like N5 DDT, it is center, but it has like a thick side and a thin side. Whereas N5 Def, it looks regular, but it's completely off center. So if you just look at the shell, it's not centered on the explosion center. And DDT versus Def, we also see differences, like with deflagration models, you see densities that remains at the core that maybe you see in the later phases. And also we see something at the edge. And if there's a detonation, these things tend to be erased. Okay, so we could see the imprint of the explosion mechanism. And that was just one scenario. These are just variants of the same kind of model. So now I want to move on to this different kind of scenario. So this is the case with two white dwarfs, so that's double degenerate. And this is not a merger, not a violent collision. One of the white dwarf will be helium ignited. Okay, and so this has been called, because this happens with the mass transfer, it's dynamically driven. It's a double generate system, a double detonation. So that's been called a D6 system. So that's the name that was put forward by Shen et al. So they found hypervelocity stars with Gaia, which could be proved, which are expected in this kind of model, because one of the white dwarf disappears, and the other one is just flying with the orbital velocity. So in this case, in this simulation, one white dwarf explodes, the other survives. So very quickly, so you see a first detonation. There's a hot spot on one of the white dwarfs. There's the first detonation that engulfs the white dwarf. You see that it makes kind of a splash at the other end. And then the blast wave is converging inside, where it triggers a second detonation that does disrupt the white dwarf. And so it's being, stellar material is being ejected and it's engulfing the companion, but you see the companion survive and it's kind of shadowing the ejecta. Okay, and so the ejecta would be pretty simple, pretty symmetrical, be it for this companion effect. So I'm looking here at the density at I think 50 seconds. And so you see this tail at the bottom from the first detonation, and you see this region that's looking a bit different when the density is more complicated, and that's a conical shadow from the companion. The companion is very nearby, you don't see it here, but so it casts a shadow on the ejecta. And we have 3D models, you can check later, but now I'm going to show again flattened out things. So at the top, it's again a slice of the density so that you can understand the inner structure of the shell. And the bottom, it's a density squared projected for the ejecta. So that's a proxy of the X-ray emission, thermal X-ray emission. And so I'm going to play the time evolution again. Before I start, so you see this. So on the left, X view, and bottom Z view, this is the tail from the first detonation. And you can see where the shadow of the companion is located at the bottom of the Y view and on the left of the Z view. So playing time now. And so you see this tail from the first detonation that was very visible at the beginning, only at the beginning. Now it's been like taken over, and you see the reverse shock in this companion cone. Dynamics are a little bit different because density is different, and it so happens that it makes you like a very straight reverse shock that's going in. And at the edge of this region, you have enhanced relational growth. And so if you look in projection, you actually see kind of a hole surrounded by a bright range. And so this is still running. So the previous ones were to 500 years, like a tycho-like edge. This one I did to thousands of years because the features are long-lasting. And so we went to the time where the reverse shock has reached the center, it's bouncing back. Okay, so just skip the very end, maybe a quick summary. So there is this tail from the first detonation. You don't see it for long, but I find it interesting because it looks like a protrusion, but really it's something that was here from the beginning that's being taken over. And the main thing is the shadow from the companion, which depends on the viewpoint. If you look along the axis, you see actually this kind of hole. But if you look sideways, you'll see an ellipse or even just a bar. And these people will be like, oh, is it colliding with something in the ISM here? The ISM is assumed to be uniform. So what you see is just an effect from the explosion of the progenitor system. And just, so we have like 1 more minute. So just to mention that this was hydro, but so we have the distribution of the elements computed from the nuclear reaction network. So I have the 3D and time-dependent distribution of the elements. And from this, we can do more. We can actually compute the thermal X-ray emission with non-ionization. So this is what's coming next. This is just an example of what we can do where I did some quick RGB composite images with some prominent lines of interest. And you see a stratification that comes from the ejecta stratification and the different thermodynamical conditions of the plasma, and you still see what I discussed. And so we're working with other groups to try to make mock observations for instruments and figuring out how to analyze this. And so it's time we have to conclude. And just for this D6 progenitor, so basically we find that the signatures that I described at the beginning, we see them, we can see them on the remnant, we can see the imprint of the first detonation. The second detonation, I didn't say it's the central density. The whole thing is off center because of the binary. And there is this conical shadow in the ejecta, and which is to be disentangled from what happens in the SNR phase and what would happen because of a non-uniform ISM, of course. So the point is you don't need a very, you don't need a complex ISM to get a complex looking type 1A supernova remnant. And so just if I have 10 seconds more, larger conclusion on the fact that we are studying 3D objects, so we should harness 3D modeling power of simulations. And the more we can compare this with the 3D structure of the SNR from observations, the better. And I will stop here.
Okay, that's thanks, Jules. Great work. In the interest of time, I'm going to allow one quick question. Is there a burning question in the room? I see Wolfgang smiling. Go ahead.
One question I had was you mentioned about the companion and leaving a shadow. I know there was some claim years ago where people told me that Chandra reduction is to blame and it's not actually a companion. And so I'm wondering, can we rule out a companion in Tycho or in 1006 because we don't see that pattern?
So I don't know if I got the question correctly.
So maybe I will. Wolfgang is mentioning that there was an observational paper claiming there was such a shadow in the type of supernova remnant, but that there seemed to be some controversy around that. And he is again asking the very relevant, negative question of can we rule out the existence of this sort of companion shadow and cavity by looking at the observations of Tycho and SM1006.
Okay, that's one good question. So I think here we're talking about Tycho in particular. So this is still a modeling work. The more detailed comparison has to be done for Tycho. I know that there's people who claim that they see there's an arc that maybe like a shadow from a companion. And so I'm not completely convinced. Certainly it doesn't match what I've been presenting. So if that would not be like a D6 kind of model. And also there has been this argument that so if there is a shadow from a companion, people were thinking if there's a companion, so it's like a normal star, so it's single degenerate. And so we know now that this is not true. So you can get a surviving companion in a D6 kind of scenario for double degenerate. So things are just getting more complicated. And so people have been looking for companions like normal star companions. And so maybe they should be looking also at surviving white dwarfs. I don't know if this is excluded or not. So I don't know. I've said a lot of things. I don't know if I've addressed the question.
Well,
So, yeah.
we should continue the discussion. I do encourage people to use both Slack and the Q&A on Zoom, because in the interest of time, we can't possibly address all the questions, but they're all important. So we should move on to the next talk, which is also a contributed talk by Cressida from Progress.
Do you need the microphone?
Yeah.
Okay. Sorry, one second. Okay.
All right. Good morning, everyone. My name is Prasida, and I'm a graduate student at Rutgers University, working with Professor Jack Hughes, whom I believe many of you here are quite familiar with. So I'm talking to you about measuring the explosion properties of young supernova remnants using the specific example of SNR 059 67.5. So there's several advantages to studying this remnant. The biggest one being that it is one of the only two supernova remnants that's been confirmed as a type 1A, and the fact that it is in the LMC, whose distance we know to very high accuracy. So I'm going to talk to you about HST observations of this supernova remnant that we conducted in 2006 and 2016. On the right, you are seeing the GIF, which shows the expansion of the forward shock in this time. So what we do is basically measure make individual 1 degree azimuthal regions, as you see in the bottom left there, and measure the proper motion and the position of the forward shock. So we end up getting 231 viable apertures. And the mean forward shock that we measure is 26.6 milliarc seconds per year, which translates to 6,200 kilometers per second at the LMC. So this is my first big slide where I have the velocity and the radius of the proper motion as a function of position. So this is a busy plot, so I will not go into too much detail, but I will say that the velocities through the eastern rim of this remnant are very much uniform. And you see a lot of structure down here in the southwest, which is where we believe it is interacting with a dense ambient medium. And you also see the radius. The remnant is also pretty elliptical, which you can see from the radius values. So I'll actually strip the remnant out from XY to R theta, so you can see which regions correspond to which part of the remnant. So we have this amazing data on the forward shock. What do we do with that? So this is where the modeling comes in. So I'm doing 1D hydrosimulations of supernova remnants evolving in a uniform ambient medium with an exponential ejector profile. So these are the two assumptions I'm making about my model. And the outputs of the hydrocode are cast into similarity solutions, Trulau and McKee, this is a classic paper. And they depend on three important parameters, which is the ejector mass, the explosion energy, and the ambient medium density. So one other thing that we do is approximate the effects of diffusive shock acceleration and try and see if there's any cosmic ray acceleration of the forward shock of this remnant. So the way we do it is to modify the adiabatic index of the material that's upstream of the forward shock. We will be talking about two cases. One is gamma 5/3, which is ideal gas, no CR acceleration, and the other is gamma equals 4/3 with a significant CR acceleration. So I've talked to you about data. I've talked to you about this model. How do we put them together? So this is where the MCMC comes in. So given a model, the MCMC algorithm samples through the parameter space to evaluate the likelihood for the model to fit the data. So the equation is long here, but the takeaway is that I'm trying to simultaneously fit for the radius and the velocity information. So of course, MCMC requires priors on parameters. So I have priors of the age between 150 and 450 years. It's flat prior, so it's equal probability for all the points. The distance is the only informed prior here. So distance a Gaussian prior with a distance at 49.27 kiloparsec, plus or minus 1 parsec, which accommodates for the thickness of the LMC disk. So the number 49.27 comes from the anchor measurement for the LMC distance, thanks to the cosmologists who care about the measuring H naught. So the actual value is 49.58. And what I do is correct for the geometry of the LMC, which reduces the distance to 49.27. Then I'm considering that the evolution is happening for every radial region individually. So every radius and velocity point is evolving independently. So I have so many data for the velocity of the forward shock and the radius. So basically, I have 44 regions for which I calculate the density. And what's really nice is that because you're also fitting for the radius, you can basically input a center value and have the MCMC calculate a dynamical center based on what it finds as the best fit for the forward shock information. Of course, I need to fix some quantities. I only have 2 sets of data. So I'm fixing the energy at 1.4 solar mass and the ejector mass, energy at 1.44 and the ejector mass at 1.4 solar mass. So let's look at results. So this is just using the forward shock kinematics. I am measuring an age of 315 plus or minus 2 years. This is how good the HST data is. It's thanks to that. And I measure the first precise measurement of the dynamical center of the remnant. As you can see, the delta RA and delta dec are at 0.1 and 0.2 arc seconds. And the dynamical center is actually within 0.03 arc seconds of the geometric center of the remnant. And I have 144 measurements of the densities at different regions around the remnant. The average value comes out to be 6.35 e to the minus 25 grams per centimeter cube. All right, so this is the plot of the density as a function of position angle that you're seeing in the blue at the top. But I will say that this is not the only solution to this problem. The other way you can do this is fix the density and vary any other quantity, let's say the explosion energy. So this is the dependence of the explosion energy if you are accounting for an asymmetric explosion. So basically the point here that I'm making is that the hydro simulations produce a circular remnant, but we know clearly that this remnant is elliptical. So in order to produce an elliptical remnant, we let the density or the explosion energy, one of these parameters, vary locally with the position angle. And one other point is that the correlation that you see between the bright regions with smaller radii and the bright regions with smaller radii and the faint regions with larger radii actually argues for a density variation instead of an energy one. So far I've talked to you about just using the information of the forward shock. What can we do? So the thing here is, if you have a measurement of any other kinematic quantity, you can pin this remnant in time, which lets you one free parameter that you can fit for. So in this case, we do exactly that by fitting for the explosion energy using the reverse shock location. I'm so glad Ivo spoke before me. So we are using the reverse shock location from Ivo's paper. So basically, we have one measurement of the reverse shock radius, one value for the, so we have several values for the forward shock radius and velocity, but since we only have one value for the reverse shock radius, I'm taking the average values for the forward shock radius and velocity. So basically, I have 3 data points. I'm fitting for three parameters, and those are the age, the explosion energy, and an average ambient medium density. So it turns out my explosion energy for this remnant is 1.30 plus or minus 0.44. So the value is really nice, but the uncertainty is quite large. And I want to say that the reason for that is because we have optical data, ground-based optical data for the reverse shock, but we have very precise forward shock information. So what I'm saying is, if we have a way to determine a more precise location for the reverse shock and reduce that uncertainty over there, we have a precise measurement of the forward shock, of the explosion energy. The caveat being, I am still fixing the explosion energy to 1.4 solar mass. Okay, let's talk cosmic rays. So here, like I said, I've done two cases for of MCMC runs. One for gamma equals 5/3, which gives me an explosion energy 1.3, which is consistent with the 91T picture. But on the other hand, for the 4/3 case, I have an absurdly large value for the explosion energy at 2.7 plus or minus 0.7. So even though the uncertainty is large here, the value 2.7, 2.8 is greater than 2 sigma away from our conventional understanding of type 1a supernovae. So what I'm doing is I'm rejecting the 4/3 model as a valid model for this remnant and saying that the CR acceleration is not very efficient at the forward shock of this remnant. Finally, let's talk about progenitor companions. So I have a precise measurement of the dynamical center, which you see in the red cross there. And I'm putting a magenta circle that is the search radius for a main sequence star. And I have another search radius for white dwarf candidates. This is directly coming from the D6 model that Gilles just spoke right before me. So that's the search radius for a star that's at 1,000 kilometers per second. So I've highlighted in dark blue right here. There's three candidates that you see inside that I don't really know what they are. But I can say that they're fainter than 27th magnitude. So we really need our telescopes to go and look in there and see what's really happening. So I will not comment on whether this is a single degenerate or a double degenerate progenitor, but I will say this, that the uncertainty in the position of a companion, if there is one, is going to depend on the astrophysics. You know, it's really what type of stars you think are potential candidates for companions, and it's not dominated by the uncertainty measurement error in the dynamical center. So, yeah. So basically, I just want to conclude by saying that we can constrain explosion properties of young supernova remnants just from shock kinematics. You don't need complicated models. So I'm not saying the models are wrong, but there is a simple way to do this as well. So this is my first paper. I've just put it on the archive this morning. So please check it out.
Okay. Are there any questions in the room? Oh, that's one. Was it Jaco?
Well, you know, the obvious thing is, of course, that you use 1.4 solar masses. You heard Ivo say, well, it was around 1 solar mass. So
That's correct. So I actually do have a backup slide for that.
Oh, there you go. She came prepared.
Yeah. So these are the results for, so I can either fix the energy and fit for the mass, or fit the mass and fit for the energy. So it turns out if I fix the energy at 1.4, my value for the ejector mass is coming around 2.02. But you see the uncertainties there are quite large. So I wouldn't trust this result as such, but you know, with better measurements of the reverse shock location, it should reduce.
is there some way to use the type 1a spectrum that we have, but it's 91T? Can we infer energy and then fix the energy?
I think that's where you're starting from, right? I assume the 1.4 and 1.4 come from the analysis we did back then.
That's right. That's right.
And this again did not include the Chandra model, so yeah, but the model that worked then, but those were the parameters that it had. Okay, I have a burning question. You can go back to your summaries, like
Oh, yes.
here, and this is bothering me a lot.
Why?
Here is why. This is an explosion of around 1700. Okay, a 91T like type 1a supernova in the LMC has a peak magnitude of -1. There is no way in 1700 that an event like this could have been missed by the bustling European explorers that were all around the southern hemisphere navigating by the stars.
Mhm.
looked for and could not find anything in the historical record that would be connected with a supernova like this. This is something that I find really strange.
I was expecting that exact question from you actually. And I actually don't have an answer for you, but Ivo and I were discussing about the same thing yesterday, and
Yeah.
what can I say? Maybe people were too busy with their lives. They didn't look at it.
Well, but if you have, for instance, settlements like Buenos Aires, Lima has horrible weather, but Buenos Aires was permanent in 1580. So you got people there, working and keeping records and navigating by the stars. I don't know.
400 years would be a problem.
Is that the reason why it's called Buenos Aires? It's quite-
It certainly has better weather than Lima. Lima is always cloudy. And Lima is the earliest European settlement that's far south in the Americas. There were others, like the Dutch were in Jakarta.
That depends on the time of the year.
Well, for a 1A in a location with no extinction, like the LNC, you would see it for months.
But it's very bright, the LC is applicable in February. So what about if it was taking place in July or August 15th?
For instance, well, the LNC is circumpolar from Buenos Aires. So you can always see that. So. Evo.
Yeah, so I estimated peak magnitude of -0.6, and so would have been the second brightest, after Sirius, the second brightest object for weeks in the southern hemisphere. But even at 400 years, which is maybe as high as we want to go in age, what you're saying that it still would have been a problem. Same
Yes,
problem.
that's what we wrote back in 2008, that 400 years was a problem, but 300 years is like a bigger
But
problem.
it's only that bright for, couple months or something. I mean, it quickly fades, right? And it might be circumpolar, but it's low on the
I
horizon.
mean, we're overthinking this, we all know that Cassie was missed, so. Okay, we do have to move on, thank you, Cassie. And,
Thank you.
I don't mean to ignore any of the questions and,
Yeah, I will
still
take
in
questions
Slack.
on Slack.
but we do have to move on. Our next talk is another contributed talk by Masahiro Ichikashi from the University of Tokyo. Masahiro
Okay,
online.
great. Oops, can you see my slide?
Yes, we can.
Okay, let's start my talk. Hello, everyone. I'm Masahiro Ichihashi, the graduate student of the University of Tokyo. In this talk, I will talk about our study and the discovery of spatial variation of electron temperature in the northwestern region of SN1006. The object of this study is that the analysis of the spatial variation of electron temperature near the shore. To complete this object, we analyze the northwestern region of SN1006. SN1006 is one of the type 1A supernova remnant first observed in 2006. It is located in 2.2 kiloparsec from the Earth, and its diameter is about 20 parsec. SN1006 is suitable for our study for mainly two reasons. First, SN1006 is located relatively near the Earth. And because of this, we can easily observe the spatial variation near the shore by using the standard spectroscopy. Second, SN1006 has the filament structure dominating the X-ray thermal emission in northwestern area. We can estimate the electron temperature directly from the spectra of thermal emission, so it is suitable environment for our study. So we measure spatial spectroscopy in the northwestern region of SN1006 with Chandler's greatest spatial resolution. We use the data observed by Chandra satellite in April 2001 and April 2012. We divide the northwestern region by 3.3 times 4 regions, like shown in left figure. And the size of each region is 140 arcsecond times 15 arcsecond, and the real length is 1.5 parsec times 0.16 parsec. The example of the extracted spectrum is shown in right figure, and the black point spectrum is the spectra from outer region, and the red point spectra is from inner region spectrum. This figure shows that the spectrum of inner region is harder than that of outer region, which suggests that the temperature decreases inwardly. Okay, from next slide, I will talk about the result of our spectral analysis. First, I talk about the result of spectral modeling. We fit all 24 spectra to observation data times 12 extracted region by non-equilibrium ionization collision plasma model. In this model, we fixed interstellar absorption by the value of previous study, 4.16 times 10 power to 20. Also, the metal abundance, especially nitrogen, oxygen, neon, magnesium, silicon, and iron are assumed as a free parameter, and all metal abundance are tied among all the regions. The result of spectral fitting is shown in these two figures. As figure shows, we find that the model in this condition explains all the data well. The special variation of estimated electron temperatures and ionization parameters shows in this figure. Left figure shows that the electron temperature increase with increasing the distance from the shock, and the right figure shows that the ionization parameter has no significant change in observed region. The consistency of the ionization parameter implies that the electron density decreases toward inside. To evaluate the variation of electron density quantitatively, we also estimate the electron density from the emission measure. To estimate it from emission measure, we assume the volume of the observation region as a sphere with the lack of the northwestern area, like left figure. The result of estimation of the electron density shows in right figure. This figure shows that the electron density decreases with increasing distance from the shock. This trend is consistent with improvement from the ionization parameters. Okay, next slide. From the next slides, we discussed the result of the analysis. First, we discussed the comparison of our observation with the analytical Coulomb scattering model. In this model, the variation of electron density shown in the slide before is considered. In this model, we assume the shock speed as 2,800 km per second, and the initial temperatures of ions is assumed from Rankine-Ironi relation. The initial temperature of electron is calculated by the ratio to proton temperature. In our study, the ratio of electron temperature to proton temperature is considered by three cases: 0.03, 0.01, and the mass ratio. The result of comparison shown in this left figure, which shows that the increase of observed temperature is lower than that estimated from Coulomb scattering model. To modify this difference, we need to consider more factors, for example, the projection effects or the variation of shock speed. In the case of considering the projection effect, the temperature of the inner region is estimated to be higher than the current observation value. Because the emission from the inner region contains the emission from the region of a similar environment to the outer region. For this reason, considering the projection effect makes the observation much better to the Coulomb scattering model. Another factor, the variation of the shock speed, is explained in the next slide. The variation of the shock speed is implied by mainly two factors. First, high density clouds exist at northwestern region of SN1006, like this green area of left figure. Also, the shock speed in northwestern region of SN1006 is about half slower than that of other region of SN1006. As the right figure shown, these two factors imply that the shock speed in northwestern region of SN1006 decreased by interaction with high density cloud. Decreasing shock speed affects the electron temperature in some way. For example, the decrease of the initial temperature of ions and electrons and the formation of high density and high temperature areas near the shock. In the future work, we are going to analyze the effect of temperature variation considering the change of these shock speed change. That's our conclusion. We analyze the special variation of electron temperature in northwestern area of SN1006, and we discovered electron temperature is found to increase inwardly on 60-axis K. The variation of electron temperature cannot explain by Coulomb scattering considering the variation of electron density. So we need to consider more factors. For example, projection effect may match observation and model, and we will consider the variation of shock speed in future analysis. That's all. Thank you.
Well, thank you, Masahiro. Beautiful timing. So questions for Masahiro? Yeah.
One other factor that might change is the abundances, because dust is observed in that region and it is destroyed on something like that scale.
Sorry, and can you tell your question more slowly, please?
So it is observed that there is infrared emission from dust in that region. And it seems as though it is destroyed on a length scale on the order of an arc minute or so. And that will change the elemental abundances of the refractory elements, silicon and iron.
Sorry, in our analysis, the element abundance is assumed as a consistent of all of regions. So I can tell you how the element abundance changes in our observation area. Sorry.
Yeah, I'm just saying that it's another variable you might consider.
Do we have any questions on, I see one on Zoom.
This is no simple question.
No one's question. Okay, is there anything in Slack? I didn't look this time.
I didn't see anything.
No?
last time.
Okay. Anybody else? If not, let's move on to the last talk of the session, which is by Masamune Matsuda. Last minute online. Here we go.
Can you hear me?
We can hear you. Take it away.
Okay. Hello, my name is Masamune Matsuda, and I am a PhD student in astrophy in Kyoto University and working with Hiroyuki Uchida and Mr. Tsuru-san, Tanaka-san, and Yamaguchi-san. And today, I'll talk about the Chandra analysis of Tycho's supernova remnant. This is a movie made from Chandra images taken in 2003, 7, 9, and 15. Because Tycho is a young SNR, because Tycho is a young SNR, the remnant is expanding with high shock velocity of 2,000 to 8,000 kilometers per second. And this image, in this image, red and green shows thermal radiation, and blue shows non-thermal radiation. As can be seen from this movie, both thermal and non-thermal radiation are bright. Focusing on this western region, we can see a peculiar structure like this image. This is called as a stripe structure discovered by Erickson et al. Recently, we analyzed the Chandra image taken in. We analyzed the stripe structure with Chandra image taken in 2003, 7, 9, and 15. And we discovered the time variability of non-thermal radiation in stripe structure. This figure shows the result of the analysis. X-axis shows photon indices, and y-axis shows surface brightnesses. For example, region 1 and 9 shows brightening and hardening, and region 7 shows darkening and softening. And when we plot the result of all of these regions, we discovered all of the stripes have time variabilities. This synchrotron time variabilities is discovered in other SNRs, such as RxJ1713, CAS-A, and G330. The synchrotron time variabilities is thought to result from particle acceleration and synchrotron cooling in amplified magnetic field. So this can reveal the real-time energy change of particles. So we wondered, how about thermal X-ray? Thermal X-ray time variabilities is discovered in few SNRs, such as CAS-A, but it will be a hint of solving the problem of electron heating mechanism. So we searched the time variabilities of Tycho. We searched the thermal time variabilities of Tycho from these movies. Apparently, this movie seems to show that the SNR is only expanding, and there is no significant flux changes. But focusing on this region, we can see the significant flux increase, like this movie. This time variability is the first discovery of the thermal X-ray brightening in Tycho's supernova remnant. Then we show the spectra of the time variable region, named as not one, and the nearby region named as ref1. Black shows the spectra of not one, and the red line shows the spectra of ref one. As can be seen from these spectra, not one is brighter than ref one in less than 1.5 kV band. And as can be seen from the ratio spectra in both panels, the energy band with high not one to ref one ratio expands to higher energy year by year. For example, in 2000, the excess shows in less than about 1 kV, but in 2015, the excess shows less than about 1.5 kV. And so we analyzed the spectra by fitting with the NEI model. The red line is a soft component, assuming as a time variable component. As can be seen from these figures, the soft component become flat year by year, and this shows the increase of increase of KTE, and we can explain the spectra with the soft component with the solar abundance. So we compared the not one with H alpha images. This figure shows the soft X-ray image and H alpha contrast. As can be seen from this figure, not one have a good correlation with H alpha. H alpha is thought to radiate by interaction between forward shock and neutral hydrogen gas. So this good correlation is a strong evidence that not one originates from forward shocked ISM. And when we see the HST image of not one, we reveal that not one have multiple filaments. So so maybe there are many dense clamps in not one. Then we discussed the origin of the time variability from the best fit parameter of the soft component. These figures show the time variability of the best fit parameter. X-axis shows times and Y-axis shows electron temperature and ionization time scale and emission measures. As can be seen from these figures, electron temperature shows significant increase, but ionization time scale and emission measure shows no significant change. From emission measures, we can estimate the density of not one as about 10 per cc. This is about 10 times denser than its surroundings. Then first, we discuss the change of ionization states. These figures show the fraction of H-like ions of neon and magnesium. X-axis shows electron temperature and Y-axis shows ionization time scale. And these contrasts show the fit results in each year. As can be seen from these figures, the H-like ion fraction increase year by year, even though there is no significant change in NET. This suggests that the ionization is occurring in not one. Then we discussed the increase of KTE. we can interpret the KT change as the result of Coulomb heating. We can write the proton temperature in shock transition. The proton temperature in shock transition is written as this formula, and the electron temperature can be written as this formula using a parameter of beta zero. Beta zero beta zero represents the efficiency of collisionless heating at the shock transition. So when there is no collisionless heating, beta zero is equal to mass ratio of electrons and protons. Then electron temperature, electrons are heated colliding with protons behind the shock. We compared the observed KT chain increase from the calculations for different beta zero. This figure shows the result of comparison with the observations and calculations. X-axis shows time and y-axis shows KTE. And these plots show the result of observations, and the lines show the result of calculation. And the red shows the result of when beta zero equal to mass ratio, and the green is beta zero equal to 0.05. Blue is 0.08. Yellow shows 0.1. As can be seen from this figure, beta zero is required to be mass ratio to 0.05 to reproduce the observed KTE change. And as can be seen from this figure, H alpha results shows beta zero of Tycho is about 0.05. So our results is consistent with H alpha results. That's conclusion. We analyzed the time variability of Tycho supernova remnant, and we discovered the electron heating of in the time variable region, and the result is consistent with H alpha observations. That's all.
Thank you. So, questions for Masamune? Oh, I see a question back there. Yes.
Hi, thank you for a very nice talk. I was wondering about your slide where you show you fit models, your non-equilibrium models, and you extract the electron density from the emission measure. You also show the ionization plate scale, which is flat with time. I was wondering if you try to compute also the electron density from the ionization plate scale to check if it was consistent with your emission measure.
Sorry, you mean?
Earlier, yeah.
You mean? Sorry, can you do that again? Sorry.
When you show your fits.
Sorry, do you mean this figure?
No.
No, it's an earlier figure.
Yeah.
Sorry. See, do you mean this?
Yes.
Okay.
And then you show the ionization tape scales and emission measures as a function of time, and you extract, you compute the electron density from your emission measures, right? And so I was wondering if you compute your electron densities also from the ionization tape scale, do you find the same electron density?
Electron density. Sorry, electron. Sorry.
Is NET from the emission measure equal to, sorry, is NE from the emission measure equal to NE from the ionization time scale?
Ionization. Sorry. you mean, you mean, so can you say that again?
The ionization timescale is NE times the age. The emission measure also has NE.
Yeah.
Do those give the same numbers for NE?
Sorry.
Maybe we can discuss it.
Yeah, maybe we can discuss this offline, so keep an eye on Slack. And oh, you want to quickly answer, or it's okay if you want to take your time and just answer on Slack.
Sorry, can I say that again?
Yeah, let's just leave that discussion for Slack, and again, remember, contribute to that if you are interested or can. This concludes the morning session. I think we should thank our speakers again.
Sorry. Thank you.